In this video, we are going to look at algebraic properties of matrix operations, specifically because there are many familiar algebraic properties of real numbers that also hold for matrices. However, there are important exceptions, such as the fact that matrix multiplication is not commutative. Also, there's no cancellation law. So for example, the matrix A times matrix B equals matrix A times matrix C does not imply B equals C. So we will look at the algebraic properties of matrix operations in this video. First, we will look at properties of matrix addition, properties of scalar and matrix multiplication, as well as distributive properties. Last, we will look at the transpose matrix and also define what it is for matrix to be symmetric. We will start with properties of matrix addition. If A, B, and C are M by N matrices, then A plus B equals B plus A. In other words, matrix addition is commutative. A plus B plus C is equal to A plus B plus C. In other words, matrix addition is associative. Next, there is the additive identity. There exists a unique M by N matrix 0, which we denote with the 0. Often it has like this script 0, which almost looks like an O, called the 0 matrix, such that A plus 0 is equal to A for all M by N matrix A. The additive inverse, that's the last property of matrix addition we will be looking at. So given an M by N matrix A, there exists a unique M by N matrix P such that A plus P equals the 0 matrix. Personally, for my class, I really don't emphasize the proofs of these properties, but just in case you need to see them, I have a couple of the proofs outlined. First, we will prove part 1, the commutative property of matrix addition. So A plus B equals B plus A, that's what we're trying to prove. So if C, that's our resulting matrix, equals A plus B, then by the definition of matrix addition, the ijth component of C is equal to the ijth component of A plus the ijth component of B. And because these are real numbers are commutative, we can switch the order B sub ij plus A sub ij. But this, for any element C sub ij, is just equal to, by the definition of a matrix addition, is just equal to B plus matrix A. I went ahead and skipped over to part 3. So there exists an M by N matrix 0 such that A plus 0 equals A. And we are just going to find the matrix, the 0 matrix, which isn't that hard. So we're going to let 0 be the M by N matrix with 0 at each entry. In other words, each entry sub ij is equal to 0. Then when we add A plus 0 equals C, then C sub ij is equal to A sub ij plus 0 sub ij, which is equal to A sub ij plus 0, and this is just equal to A sub ij, which is equal to A. The next theorem we will look at is one that gives us properties of scalar and matrix multiplication. So first, if A, B, and C are M by N, that's A, N by P, that's B, and P by Q, that's C, matrices, respectively, then A times B multiplied by C is equal to A times B times C. And if R, so in other words, we have this associativity of multiplication. If R and S are scalars, then R times SA is equal to RS times A. And then last, we have R times AB is equal to R times A times B, which is equal to A times R times B. And again, in my class, I don't really emphasize these proofs, but just in case, I will do one or two of them. But before I do a proof, let's just do one quick example. So here we have A is the matrix 1, 2, negative 1, 3, and B is equal to 2, negative 1, 3, 1, negative 1, 1, and C is equal to 3, 1, 2, negative 2, 1, negative 1, 4, negative 2, and negative 1. Then we can multiply AB. So here's my matrix A, matrix B. When I multiply, I get 4, negative 3, 5, 1, negative 2, 0. I can also multiply B times C here. So I have matrix B here, matrix C, and that gives me 20, negative 5, 2, 9, negative 2, 2. So now I'm in a position to verify that A times B times C is equal to A times B times C. In other words, the associativity of matrix multiplication holds. So I'm going to look at AB and I'm going to multiply by C. So here's AB, here's C, and I do my multiplication. I get 38 minus 9 times 6, 9 and 6, 7 minus 1 and 4. And then I have A, which is over here, times BC, which I pulled from over here, and I get 38 minus 9, 6, 7 minus 1, 4. And you can see that the A times B times C is equal to A times B times C. And now that we've done a quick example, let's do the proof of this associativity of matrix multiplication. So AB, so if A is an m by n and B is an n by p, that means AB is going to be an m by p. And then AB times C, since C is p by q, that means that result is going to be m by q. And then let's just check the size of this matrix, just to make sure at least they have the right sizes. So BC, B is n by p and C is p by q, so our resulting matrix is n by q. And then A times BC is going to be, A is m by n, so then our resulting matrix is going to be m by q. So these two match up, so at least we have some hope of having equality. And just to look at the m by q, because it's good to remember, so we're going to go across, so we're going to have q columns and m rows. So m rows, q columns, so it looks like this. And to do this proof, what I want to show is the i-th element of AB times C is equal to the i-th element of BC times A. So essentially, element by element, they're the same. So we're showing equality of every component. We are going to start with AB. Let's just assume we have AB, and then we have C. So the i-th component is equal to, and just looking at this, remember we said that AB is going to be m by p. So it's going to have m rows, p columns. And now when I look at C, the matrix C is p by q, so it's going to have p rows and q columns. I had to change this so it looks a little messy. So what we're going to do when we multiply AB times C is we're going to go down each row, so index from 1 to p, and then we're going to multiply down the column from 1 to p. So my index is going to go k equals 1 to p of AB ik times c kl. Remember how the index in here is the k is going from 1 to p for AB, and this k is going from 1 to p going down the columns, which is why the index k is here in the first element. And then the L is just matches here, and the I matches here. And this comes just from the definition of matrix multiplication. But to get my indices right, I kind of drew these two matrices so I could get my index correct. So now, if I want to have this multiplied, I want to go ahead and expand my AB. So outside, I have my k equals 1 to p, I have my AB, and then I have c to the kl. But now I want to expand my index for AB for the ikth element. So again, our AB, we want AB to the ik. And just to remind ourselves how the index goes for A times B, A has m rows and columns, and B has n rows and p columns. So we're going to go across here from A11 up to A1n, and we're going to multiply down the columns, which is from B11 to Bn1. So my index, I just need to choose a letter. So I chose S, and you can choose whatever letter you want, but preferably not the I, the K, the L. So we're running out of letters, but I chose S. So S now is going to go from 1 to n, because again, we're going across to multiply A times B, we're going across the n columns and down the n rows. So S goes from 1 to n, and A goes from IS, B, S, K. And again, because we want the ikth element here. So we're almost done with this. We can now combine these, we can pull this into this summation. So we have K going from 1 to P, S going from 1 to N, A, IS, B, SK, and C, KL. We are going to do something similar now with A times BC. We want the ILth element. So just to remind ourselves, A looks like this is M by N, M rows, N columns. And then BC, we had calculated that here. That's N by Q. So N rows, Q columns. So our index, when we multiply, we're going to go across the N columns and multiply by the N, each of the, well, across the row. So N entries across the row and N entries down the columns. So our index, and this can be any letter, but I just chose T, is equal 1 to N. So our ILth element is AIT times BC TL. Okay. And that is going to equal to, and now we want to expand our BC. Expanding our BC, so since B is N by P and C is P by Q, we're going to be expanding over the index from 1 to P. So again, I chose another letter, R equals 1 to P, B sub TR times C sub R L. And again, we're trying to get the TL term, which is why we have T and L here. And again, we can also move this inside the A sub IT, inside the sums. So we have the sum from T equals 1 to N, R equals 1 to P, the A sub IT, B sub TR, C sub RL. So this looks a lot like this. It's just that I had named my, I just kept using new letters. I can actually rename so that they look more similar. So I'm going to rename T, and I'm going to rename it as S. So instead of T going from 1 to N, I'm going to have S goes from 1 to N, and then I have to rename my T here. So I have AIS, my BSR, and CRL. Except also, you can see, I also renamed R to be K. So now K goes from 1 to P, and that's how I get my TR becomes BSK, and my CRL becomes CKL. Now these two are looking really close, except these summations are in different orders, but that's okay. I can change the order of my summation, and if you've done classes in summation, then you can prove it if you want, or you can take my word for it. So I can change the order of the summations, and then I have finished my proof. The next proof of part 2 is much easier because it involves scalars. So if I look at, if D is equal to S times A, then D sub ij, that element is equal to S times A sub ij. And then if I let E be the matrix R times SA, then the E sub ijth element is equal to R times the S sub Aij. And then I can just group, because these are real numbers, I can group R and S separate from the Aij. And the Aij is just my matrix A. The next theorem I have are the distributive properties. So if A and B are M by N matrices and C is an N by P matrix, then A plus B times C is equal to AC plus BC. And if A is an M by N and B and C are N by P, then A times B plus C is equal to AB plus AC. And if R and S are scalars and A is an M by N, then R plus S times A is equal to R times A plus S times A. And if R is a scalar and A and B are matrix, then R times AB is equal to RA plus RB. And one thing to note about these last two, we have mixed uses of the sign plus. So sometimes this plus sign is used to denote addition of real numbers. So for example, R plus S, that's the addition of real numbers. But we also have this other operation here, which is the addition of two matrices. And so it's formally it's a different operation since it operates on different types of elements. If I wanted to prove part 1, so a plus b times c and ac plus bc, I would have to first confirm that these two both have the same dimensions and they are both m by p, so that's good. And if I let q equals to ab, where q is equal to the matrix q sub ij, then the rs component of qc is equal to the sum from k equals 1 to n, q of rk, c of ks. So that means if I look at this summation, q can be broken down into ark plus brk, and then I have my cks. And now, because these are just real numbers, I can distribute real numbers, and then I get ac plus bc. Now that we've gone over our algebraic properties, we will look at the transpose matrix and the definition of a symmetric matrix. So the definition of the transpose of a matrix, so if A is the matrix with components A sub ij and it's m by n, then the transpose of A, denoted with this A superscript t, is the n by m matrix such that AT has components B sub ij, where B sub ij equals A sub ji. So essentially you flip the rows and columns. So for example, if A is equal to the matrix 1, 3, 7, 2, 1, 4, this first row becomes the first column, and the second row becomes the second column. Or looking at one of the components, for example, A2, 1, the second row, first column, which is equal to 2, and the transpose, that will be A1, 2. So the first row, second column, is equal to 2, right? So it just kind of switched it. So we have a theorem. If A and B are m by n matrices and C is n by p, then A plus B transpose is equal to A transpose plus B transpose. AC transpose is equal to C transpose A transpose, and A transpose transpose is equal to A. We will start with the proof, this first proof, part 1, where A plus B transpose is equal to A transpose plus B transpose. So A is the matrix with components A sub ij, and B is the matrix with components B sub ij. So A plus B is equal to A sub ij plus B sub ij. And A transpose is equal to A ji, B transpose is B ji. So A plus B transpose, here we have A plus B transpose is equal to, switching the j and the I, A ji plus B ji, which is simply equal to A transpose plus B transpose. For the second proof, this part 2, AC transpose equals C transpose times A transpose. First, we want to note that they both have the same, that the AC transpose and C transpose A transpose both are n by p matrices, so they have the same dimension, which is good. The next thing we want to note is the ijth entry of AC transpose is the jith entry of AC. And when we look at AC, the jth entry is equal to the sum from I, from 1 to n, A, jk, c, ki. Now that we've looked at AC transpose, let's look at this part here, the C transpose, A transpose. So if we want to look at, when we multiply these out, we're going to multiply rows of C times columns of A. So if we look at the ith row of CT, C transpose, that's actually the ith column of C written as a row. So here's the ith column of C written as a row. So that's the ith row of C transpose. While the jth column of A transpose is equal to, here, it's the jth row of A written as a column. So here's the jth row of A, and I've made it into a column now because it's the transpose. So when I multiply and want the ijth column of C transpose A transpose, I have my C transpose times A transpose, which will give me this C1I times AJ1, C21 times AJ2, etc., which is equal to the summation from k equals 1 to n, cky, ajk. And now because I can switch the order, since these are just two real numbers, I can switch their order. And now I have this, which I got from C transpose times A transpose, is equal to this summation, which is what I got from AC transpose. And therefore, AC transpose is equal to C transpose A transpose. And one more fact about transpose before we go on to symmetric matrices. So we can transpose vectors. So if x is the vector 1, negative 3, 2, and y is the column vector 1, 2, 1, x transpose is equal to the row 1, negative 3, 2, and then I can multiply x transpose times y. So here's x transpose times y, and that's equal to 1 times 1 plus negative 3 times 2 plus 2 times 1, which is equal to negative 3. And you might recognize this as the dot product of x dotted with y if you've had vector calculus before. So that means that x transpose y, I can write it in this summation formula, which is also known as the dot product. And one of the big applications of the dot product is Euclidean length, where the length of or magnitude of x is equal to the square root of 1 x1 squared plus x2 squared all the way up to xn squared, which is just equal to the square root of x transpose times x. A quick example is if I have my x vector is equal to negative 2, 3, 2, and my y column vector is 1, 2, minus 1, I can find x transpose times y, the magnitude of x, and the magnitude of x minus y. So x transpose times y is this row vector, negative 2, 3, 2, times the column vector 1, 2, negative 1. So I get negative 2 times 1 plus 3 times 2 is 6 plus 2 times negative 1 is minus 2, which is equal to positive 2. Did I do that addition right? Yes, I did. Okay. So then the magnitude of x is equal to the square root of x transpose times x. So here I have x transpose, which is negative 2, 3, 2, times x, negative 2, 3, 2. So I get my 4 plus 9 plus 4 is the square root of 17. And then x minus y, when I subtract x minus y, I have negative 3. 3 minus 2 is 1. 2 minus negative 1 is 3. And I can take the magnitude of that, which is x minus y transpose, which is negative 3, 1, 3, times x minus y, which is negative 3, 1, 3, and I get 9 plus 1 plus 9 is square root of 19. And then finally, our last topic is definition of a symmetric matrix. So a matrix A is symmetric if A is equal to A transpose. So for example, A here is equal to 1, 2, 2, 3. If I make my 1, 2, this row into my first column, 1, 2, and I make this row 2, 3 into my next column, 2, 3, you can see that A is equal to A transpose, so A is symmetric. If I look at B on the other hand, which is the matrix 1, 2, 1, 2, if I take this first row 1, 2 and make it my first column 1, 2, my second row, which is 1, 2, make it my second column 1, 2, you can see that B does not equal B transpose, therefore B is not symmetric. And one other note, to be symmetric, you must have a square n by n matrix. Visually, you can see if a matrix will be symmetric by looking down this main diagonal. So if you kind of go from one corner to the next, that's the main diagonal. If it's symmetric, your matrix will have symmetry across the axis. So here, these two are equal, these two are equal, and these, so the 3's are equal, the 1's are equal, and the 2's are equal. So if I take A transpose, you can see it's equal to A, right? Whereas here on B, I look over the main diagonal, and across the diagonal, you have things that are not equal. So negative 1 is not equal to 2, and 5 is not equal to 2, and 2 is not equal to 0. So when you look at B transpose, you can see you're not going to get something that's symmetric. So now we've gone over our main topics. First were properties of matrix operations for matrix addition, scalar and matrix multiplication, and we looked at the distributive properties. We looked at the definition of a transpose matrix, where we essentially make each row into the columns, and we said that a matrix is symmetric if A is equal to A transpose. And that's it for this video. Thank you for watching.